Hello students. Welcome to our Senior Secondary School 2 Physics lesson. Today, we will be learning about conservation of mechanical energy. But before we proceed, let's quickly recap what we learned in our previous lesson. In our previous lesson, we defined friction. We explored the types of friction. We understood the methods of increasing and reducing friction. We also went ahead to describe the advantages and disadvantages of friction. And it was really interesting. Before we begin today's lesson, let's take a quick rundown of our lesson objectives. By the end of today's lesson, you will be able to define mechanical energy, explain the concept of kinetic and potential energy, understand the principle of conservation of mechanical energy and its applications, and solve quick examples. Are you ready? Let's get started. Energy is all around us, and understanding how it is conserved helps us explain many real-world phenomena. What is mechanical energy? Mechanical energy is the sum of an object's kinetic and potential energy. Kinetic energy is energy in motion. Example, a moving car. Potential energy is the energy stored due to an object's position. Example, water stored in a dam or a stretched rubber band. Formula for kinetic energy is: kinetic energy equals 1/2 mv square, where m is mass of the object measured in kilograms, and v is velocity measured in meters per second, and 1/2, a constant factor that comes from the derivation of kinetic energy in physics. While formula for potential energy is: potential energy equals mgh, where m is mass of the object measured in kilograms, g is acceleration due to gravity, which is 9.8 meters per second square on Earth, and h equals height of the object measured in meters. Let's learn about the law of conservation of mechanical energy. The law of conservation of mechanical energy states that in the absence of external forces like friction, the total mechanical energy of a system remains constant. This means that energy cannot be created or destroyed, it only changes forms. Mathematically, this is written as kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. This simply means initial mechanical energy equals final mechanical energy. This principle applies to many real-life scenarios. Let's look at some examples. A roller coaster. At the top of a hill, it has high potential energy. As it comes down, this energy turns into kinetic energy, making it speed up. Then, as it climbs the next hill, kinetic energy turns back into potential energy. This is why roller coasters don't need engines after the first drop. They rely on energy conservation. Hydroelectric power plants. Water stored in dams has potential energy. When released, it turns turbines, converting potential energy into kinetic energy, generating electricity. Understanding mechanical energy helps engineers design safer roller coasters, efficient power plants, and effective machines. It is also important to note that, in the real world, mechanical energy is not always perfectly conserved. Why? Because of friction and air resistance. For example, when you are cycling, your bicycle has kinetic energy due to its motion. When you press the brakes, friction between the brake pads and the wheel slows the bike down. So, while the total energy in the universe is always conserved, mechanical energy can be transformed into other forms, like heat or sound energy. Let's solve examples calculating kinetic energy and potential energy. A car with a mass of 1,500 kilograms is moving at a speed of 20 meters per second. Calculate its kinetic energy. Listing the variables. M equals 1,500 kilograms. Mass of the car. And V equals 20 meters per second, velocity of the car. Solution. Substitute the values into the equation. Using the kinetic energy formula. Kinetic energy equals 1 over 2 mv square. Kinetic energy equals 1 over 2, bracket m, which is 1,500 kilograms, bracket velocity which is 20 meters per second squared. Kinetic energy equals 1 over 2 bracket 1,500 kilograms, bracket 20 meter per second squared, which is 400 meter square, second square. Kinetic energy equals 1 times 1,500 kilograms, times 400 meter square, second square, divided by 2. Kinetic energy equals 1 times 1,500 kilograms, which is 1,500 kilograms, times 400 meter square, second square. That gives us 600,000, divided by 2, which is 300,000 joules. Therefore the kinetic energy of the car is 300,000 joules. Let's solve an example calculating potential energy. A 10 kg object is lifted to a height of 8 meters above the ground. Calculate its potential energy. Take G equals 9.8 meters per second square. Listing the variables. M equals 10 kilograms. G equals 9.8 meters per second square, acceleration due to gravity. And H equals 8 meters. Solution. Substituting the values into the equation. Potential energy equals mgh. Potential energy equals m, which is bracket 10 kilograms. Bracket g, which is 9.8 meters per second square. And h, which is bracket 8 meters. Multiply all 10 kilograms times 9.8 meters per second square times 8 meters, which gives us 784 joules. Therefore, the potential energy of the object is 784 joules. It is not too difficult. Now it's your turn. Here are 2 quick practice problems. Give them a shot. Remember to pause the screen and solve the problem. Great job so far. Let's recap. Mechanical energy is the sum of kinetic energy and potential energy. Conservation of mechanical energy states that, in the absence of external forces, like friction, the total mechanical energy remains constant. Understanding mechanical energy helps engineers design safer roller coasters, efficient power plants, and effective machines. In our next lesson, we will be talking about heat energy, temperature, and its measurements. Well done. You've come to the end of this lesson. Keep practicing what you've learnt. I will see you in the next lesson.